Hi, my name is Eleftherios Kosmas and I will present our work where we study the performance power of software combining on designing recoverable data structures. The recent availability of byte-addressable non-volatile main memory, in short NVMe, combines the performance benefits of conventional DRAM with the durability size and low cost of secondary storage. This enables the design of efficient recoverable concurrent data structures, since it allows recovery after a crash to be performed by directly fixing the persistent in-memory representation. When designing recoverable algorithms, which are also known as persistent, the main challenge stems from the fact that data stored into CPU registers, caches and DRAM are volatile. Therefore, in order to survive after a crash, this data must be flashed to NVMe using persistence instructions such as flash and fence, which however are expensive in terms of performance. This is the reason why, despite many efforts, recoverability comes at an important cost even for fundamental data structures such as stacks and queues. Therefore, designing recoverable implementations with low persistence overhead is of high importance. In this work, we designed highly efficient recoverable synchronization protocols, and based on them, we built fundamental data structures such as stacks and queues. We present both blocking and wait-free implementations. Experiments show that our protocols outperform by far many recently proposed recoverable universal constructions and software transactional memory systems. In comparison to best competitors, you may see in this table that our performance improvement is significant. Based on these protocols, we built highly efficient recoverable stacks and queues that outperform all the previous recoverable implementations of such data structures that we were aware of at the time of the submission. Specialized recoverable implementations are also included. We have compared our implementations against many competitors, as you see here, and our implementations not only outperform them, but often also guarantee stronger consistency properties. Our key idea is to exploit the power of the software combining technique to implement efficient recoverable data structures. To understand why this is a promising approach, let's have a quick overview of the basic steps and the main advantage of a combining protocol. To facilitate the discussion, let us consider two threads that want to push an element into a stack. Using a conventional lock-based implementation, each thread must acquire the lock before pushing its element. On the other hand, a software combining implementation maintains an announce array with one slot for each thread. Each thread now starts by announcing its own request in its dedicated slot and then attempts to acquire the lock. The one that succeeds, T1 in this example, becomes the combiner and applies both its own request and any other currently announced request, that is the one by T2 in this example. Additionally, T1 computes the response of T2's request. On the other hand, T2 busy waits until T1 releases the lock, and when this happens, it reads and returns the response of its served request. Notice that the combiner served both requests by acquiring the lock only once. This reduces the synchronization cost in comparison with the previous simple scheme where each thread must acquire the lock in order to access the stack. Let us now discuss why the software combining technique is a promising approach for achieving recoverability by adding persistence in the previous scenarios. Starting again from a conventional recoverable lock-based implementation, it would require from each thread to persist at least the modifications made by push. In current machines, a persist operation usually contains two instructions, for instance a flash and a fence. However, using the software combining technique, these two persists are only performed by the combiner. This allows to achieve reduced persistence cost in existing NVMe technologies. Specifically, instead of having each thread executing one fence per request, the combiner can persist all the requests it applied using only a single fence instruction. Moreover, the combiner can store multiple nodes into a single cache line, thus reducing the number of flash instructions. Additionally, it can make use of an appropriate memory allocator to allocate and persist consecutive memory addresses. This is highly beneficial on current NVMe's, for instance on Intel Optane. Using the combining technique, the combiner can completely avoid applying two requests that neutralize each other, for instance a push and a pop operation, a technique also known as elimination. Finally, it is known that the software combining technique works well for highly contented data structures that have a small number of synchronization points, for instance for fundamental data structures such as stacks and queues. For these reasons, the combining technique is a promising approach. You may see here our results. They reveal the power of software combining on designing low-cost recoverable synchronization protocols and data structures. Now I am going to describe in more details PBComp, which is our blocking solution. Although combining protocols are simple in their nature, their design decisions should be taken carefully since they may have crucial impact on performance. These design decisions include the data structure used to store the announced requests and the lock implementation that the threads access to decide which one will become the combiner. PBComp maintains an announce array, and in order to keep the persistency cost low, both the announce array and the lock are maintained in volatile memory. Additionally, to reduce synchronization overhead, our lock implementation is simple and has the property that a thread that fails to acquire the lock waits only for the current combiner that holds the lock to release it. Another design decision that is important in terms of synchronization and persistence cost is the mechanism used by the combiner to discover the requests that have not yet been applied, so that it applies them. These requests are called active. To be able to determine the active requests, PBComp uses a lightweight technique that employs 2 bits for each thread, an activate and a deactivate. If these 2 bits are not equal, the corresponding thread has an active request. Each of these bits is flipped when the request is announced and after it is served respectively. The activate bits are maintained in volatile memory while the deactivate bits are maintained in NVMe. Another design decision regards the mechanism for storing and retrieving the responses of the served requests. PBComp implements this by maintaining in NVMe an array with 1 slot for each thread. This array of responses, together with the deactivate bits, are maintained in NVMe so that while recovering after a crash, it is possible to determine whether a crashed request took effect and if so, return its response. This property is known as detectability and allows a thread to recover and continue its execution after a crash. A non-detectable but still recoverable version of PBComp could maintain these arrays in volatile memory, thus further reducing the persistence overhead. I will now describe how a combiner applies requests in PBComp, which is another important design decision that greatly affects the synchronization and persistence overhead. PBComp maintains a set variable, charState, to index the state of the implemented data structure. The combiner starts by creating a private copy of this state and applies all the active requests on this copy. After completion, the combiner atomically switches charState to index the new copy, indicating that it stores the current valid state of the implemented object. Considering persistence, the private copy of the state is persisted before updating charState, and the new value of charState is persisted before the combiner releases the lock. To reduce the cost of persisting the private copy of the state, an optimization can be applied for data structures with a small number of synchronization points by copying only the state of these points. Stack is one such data structure since top is the only point of synchronization, and we applied this optimization to get PBStack. Regarding persistence, in PBStack only top and any newly allocated nodes are persisted, thus avoiding to persist the entire state of the simulated stack. I would like to highlight that copying the state of the data structure is one of the most crucial design decisions of PBComp in terms of performance. It allows to make use of an appropriate allocator in order to allocate and persist consecutive memory locations for the private copy of the state. We better enhance this by storing all other persistent metadata of PBComp together with a private copy. Additionally, it allows all updates on the simulated state to become visible with a single atomic instruction, which allows us to ensure crash resistance easily. This is so since a crash that occurs either before or after this atomic update is persisted retains the data structure in a constant state. Specifically, the effects of all requests that have completed before a crash are reflected in the state of the data structure upon recovery. This is actually what the durable nearability correctness property requires. Therefore, PBComp supports durable nearability without requiring any action upon recovery, a property known as null recovery. Additionally, it supports detectability with only a single check to determine if a request has been served and if so, retrieve its response. Since I don't have enough time to present in detail the rest of our results, I will now briefly present their key points, highlighting key differences or similarities with the implementations of PBComp and PBStank. More details about our results can be found in the full version of our paper. We have implemented a blocking recoverable queue called PBQ that is built using two instances of PBComp in order to achieve better performance. The first instance coordinates accesses on the head of the queue, while the second coordinates accesses on the tail. Similarly to PBStack, each of these instances copies only the state of the synchronization point it coordinates, that is head and tail respectively. Additionally, we implemented a weight-free combining protocol called PWFComp, which borrows and extends ideas from PBComp and PSIM. In PWFComp, several threads may concurrently attempt to become the combiner. This results in increased persistence cost because more than one threads apply the persistence instructions. So we had to implement additional techniques to reduce this cost. We provide the details in the full version of the paper. Based on PWFComp, we implemented a stack and a queue called PWFStack and PWFQ respectively. Both of them copy only the state of their synchronization points, with PWFQ additionally using two instances of PWFComp similarly to PBQ. I will now present the performance analysis of our implementations. You may see here the Intel machine we worked on and how it is configured. The machine has 96 cores and 1 TB Intel Optane NVMe. To test our recoverable combining synchronization protocols, that is PBComp and PWFComp, we first use a synthetic benchmark where each thread repeatedly executes an atomic fetch and multiply operation. To simulate a more realistic workload, each thread adds a randomly produced workload between consecutive operations. We compare the performance of PWFComp and PBComp against both universal constructions and software transactional memory system. The x-axis shows the number of threads and the y-axis shows the throughput in millions of operations per second. This figure shows that PBComp is more than 4 times faster and PWFComp is almost 3 times faster than their best competitor, which is RedoOpt. Let me point out that the RedoOpt implementation incorporates a combining technique like our protocols and borrows ideas from PSIM like PWFComp. These performance gains are achieved given that our protocols satisfy detectability, whereas the competitors satisfy only weaker consistency properties. Here you can see our experiments for recoverable queues and stacks. Our benchmarks execute pairs of NQDQ and push-pop operations respectively. As you can see, we have experimented with many competitors, basically with all implementations that we were aware of and could have access to their code. These also include specialized implementations, specifically the Friedman et al. Recoverable queue, that is FHMP in the figure, and the DFC recoverable stack, which is based on flat combining. You can see that we are better than all these algorithms. More specifically, PBQ and PWFQ are more than 5 times faster than their best competitor, which is RedoOpt, and PBStack outperforms its best competitor, that is DFC, by a factor larger than 4. But why do we see this good performance? The main reason is that the synchronization cost of our protocols is kept low without paying significant persistence cost. To figure this out, we conducted a series of experiments that can be found in the full version of the paper. Our work has revealed the power of software combining on designing low-cost recoverable synchronization protocols and data structures. We have presented two recoverable synchronization protocols using the software combining technique, PBComp and PWFComp, which are blocking and weight-free respectively. On top of these protocols, we have built stacks and queues. Our implementations are many times faster than the collection of competitors we have studied, which often satisfy only durable inertiability, while our results satisfy also detectability. In this work, we consider the memory reclamation to be an orthogonal problem and we haven't made a big effort to address it. However, after the submission, we have solved this problem and we will soon archive a new version presenting our new results, which again shows significant performance benefits in comparison to all the tested competitors. Thank you.